Welcome to another lesson from PCB Hub. Today, we are going to uncover the true physics of return current, a concept that defines signal integrity in high-speed design. Most PCB designers know that return current flows under the signal trace. But have you ever wondered why? Is it because electrons choose the shortest path? Or is something deeper happening? Let's visualize what really happens inside a PCB. I'm Shilpa, and in this lesson, we'll move beyond the common myths. We'll explore how electromagnetic fields, not just drifting electrons, dictate the behavior of your signals. By the end, you'll understand why solid reference planes are non-negotiable for high-speed performance. Many engineers imagine that current simply flows through the trace and returns through any convenient broad path in the ground plane. At low frequencies, this might be partially true, but high-speed signals behave very differently. To understand why the myth is wrong, we need to look at what's actually happening at the atomic level. We often think of signals as electrons racing through copper, but the reality is much more interesting. Electrons inside copper move surprisingly slowly, just a few millimeters per second. Yet, signals travel at nearly the speed of light. This tells us that the signal energy is not carried by individual electrons racing through the conductor. It's carried by something else entirely. This brings us to the most important realization in PCB design. The energy is in the field. The copper traces we lay out are not just pipes for liquid electrons. They are waveguides for electromagnetic energy. The real signal energy travels in the electromagnetic field between the signal trace and its reference plane. The copper simply guides that energy. It is this field coupling that forces a corresponding current to flow in the reference plane directly beneath the trace. If the energy is in the field between the trace and the plane, then every trace is essentially half of a capacitor. This distributed capacitance is what allows the return current to follow the signal without direct contact. A signal trace above a ground plane behaves like millions of tiny capacitors connected together. Whenever the voltage on the trace changes, the electric field between the trace and the plane changes as well, inducing a movement of charge in the plane. But how does current cross the insulating dielectric? The answer lies in Maxwell's equations. We call this phenomenon displacement current, and it's the key to maintaining a continuous return path. Electrons cannot travel through the PCB dielectric. Instead, a changing electric field creates displacement current. This is how the signal trace remains electromagnetically connected to the ground plane, ensuring the return current stays tightly coupled to the signal. So, why doesn't the return current take the shortest physical path back to the source? Because at high frequencies, the path of least resistance is actually the path of least inductance, and that path is directly under the trace. The return current naturally concentrates beneath the signal trace because this creates the smallest possible loop area. Smaller loops mean lower inductance, lower impedance, and crucially, lower electromagnetic radiation. Nature always takes the path that minimizes stored magnetic energy. Understanding this makes it obvious why split ground planes are so dangerous. If you force the field to detour, you force the return current to detour, and that's when your signal integrity begins to fail. When a signal crosses a split in the reference plane, the return current can no longer follow directly beneath the trace. It is forced to detour around the gap, increasing inductance and creating significant EMI problems that can interfere with the rest of your board. To summarize, return current does not follow the shortest physical path. It follows the electromagnetic field. It naturally stays beneath the signal trace to minimize impedance. Mastering this is the first step toward professional high-speed design. Thanks for watching. I'm Shilpa BB, and I'll see you in the next lesson. Design, learn, and innovate. Subscribe for more PCB design and signal integrity tips.